an AI-generated post for your viewing pleasure. Unlocking the secrets of adversarial training, a new paradigm for neural networks. What if I told you that the way we train artificial intelligence to resist harmful attacks could be fundamentally flawed? Recent findings reveal that traditional adversarial training methods may lead us into a trap known as catastrophic overfitting, leaving our AI models vulnerable when they should be stronger than ever. Buckle up as we explore a game-changing approach that redefines how we build resilient neural networks. Before we jump into the nitty-gritty of this research, let's take a moment to appreciate the broader impact of what we're about to explore. This study doesn't just scratch the surface. It could reshape the future security protocols of artificial intelligence and various applications, from image recognition to autonomous systems. In the world of artificial intelligence, deep neural networks have made waves, achieving remarkable results in diverse fields, such as computer vision and natural language processing. However, there's a shadow looming over these advancements: adversarial attacks. These crafty perturbations subtly alter an AI's inputs, prompting it to misclassify or behave unexpectedly. Defending against these threats simplifies to one key strategy: adversarial training. But what happens when this tried-and-true method inadvertently leads us into a quagmire called catastrophic overfitting? Enter a breakthrough from a team of researchers at Southeast University who have ventured deep into this rabbit hole. By shining a light on the intricacies of adversarial examples, those tricky inputs engineered to deceive AI, the researchers discovered patterns that could hold the key to overcoming the challenges of company. They've developed a new strategy termed Taxonomy-driven fast adversarial training, TDAT. As we unpack this fascinating journey, we'll see how their discoveries may redefine training techniques and enhance the reliability of neural networks in real-world applications. Before diving in, let's break down some essential concepts. At the heart of this discussion is adversarial training, a method that bolsters the resilience of neural networks against adversarial attacks by deliberately training them on perturbed inputs. Central to this is the distinction between single-step and multi-step at methods, with single-step at promising efficiency but plagued by catastrophic overfitting. This KO occurs when models perform well on training datasets but falter significantly against more complex, multi-step attacks. Another important term is adversarial examples, AES, which are inputs specifically crafted or modified to fool machine learning models. Understanding how AES interact with neural networks will help us unravel the remarkable findings of this research paper, particularly how a well-structured taxonomy of AES plays a role in counteracting company. Stick around as we tackle these concepts and explore the revolutionary approach introduced in the study. Now that we have a strong foundation, let's shift our focus to the key contributions of this study. We'll take a closer look at the methodology behind TDAT and how it sets itself apart from traditional adversarial training techniques. The crux of the study lies in addressing the CO issue that often strikes when training neural networks through adversarial methods. The researchers found that the accuracy of models can fluctuate drastically, leaving them vulnerable not just to single-step attacks, but to more complex multi-step ones as well. Their findings indicate that CO is tied to the reduction in model generalization, which can spiral quickly through just a few training batches. They introduced a new taxonomy of adversarial examples, breaking them down into 5 categories based on their interaction with model classification. Such a categorization reveals not only how different examples contribute to CO, but also highlights how this previously ignored factor could be employed to build more resilient training methodologies. The introduction of batch momentum initialization within TDAT further enhances the diversity of these generated adversarial perturbations without demanding excessive computational resources. TDAT leverages a principle known as label relaxation, which enables the model to adjust its learning process in the face of noisy or difficult examples better, ultimately reducing the impacts of misclassifications on the training stability. The key takeaway? This new strategy achieves state-of-the-art accuracy across prominent datasets, showcasing that it is possible to bolster robustness without incurring hefty computational costs. Moreover, This methodology hints at a potential universal application across various machine learning tasks, paving the way for a new standard in training resilient AI models. Now that we've unpacked the technical contributions of the study, let's discuss how these findings relate to existing research and what they mean for the future of adversarial training. The introduction of TDAT is a significant leap forward in the management of adversarial training. While traditional methods often struggle with resource limitations and result in performance trade-offs, TDAT's approach is grounded in clever adaptations that enhance both the robustness and efficiency of neural networks. However, it's essential to recognize that the study presents an overly optimistic view of the improvements achieved by TDAT without sufficiently discussing potential limitations or negative trade-offs. For instance, while the study highlights robust accuracy improvements across various datasets when subjected to projected gradient descent (PGD10) attacks, it does not adequately address how these improvements translate into real-world applications, where the balance between speed and accuracy is crucial. Moreover, while the authors assert that TDAT alleviates catastrophic overfitting, they do not quantify the potential trade-offs in model complexity or interpretability that could arise from implementing such a method. A more nuanced discussion of these aspects would provide a clearer picture of the method's overall effectiveness. The findings open avenues for future exploration. For one, the interplay between accurately classifying both clean and misclassified examples could lead to even superior performance. Additionally, the research sheds light on the need for better dataset engineering that not only accommodates but leverages misclassified examples. Observing the effects of label flipping and how misleading inputs can still contribute positively to model resilience indicates a need for novel training and data management strategies. This is a wake-up call for researchers and practitioners alike. Rethink the classification processes we use in adversarial training. The work presented here emphasizes that understanding the adversarial example taxonomy can lead us to better utilize our datasets. It's time to capitalize on every aspect of our training data for more effective machine learning. Continued exploration in this area could yield pathways to creating AIs that not only withstand threats, but also adapt and learn from them, ultimately enhancing their utility across a spectrum of real-world applications. As AI continues to reshape industries and our daily lives, ensuring the security and resilience of these technologies is paramount. The work presented by Kun Tong and colleagues is a beacon of hope in combating adversarial threats by introducing a fresh, effective approach to adversarial training. With TDAT, we're not only addressing the pressing issue of catastrophic overfitting, but also redefining our understanding of how adversarial examples can be harnessed more effectively. However, the practical implementation of TDAT across various architectures and datasets remains an area that requires further exploration and clarification. As researchers strive to enhance the robustness of neural networks, integrating these findings into existing models could pave the way for an era where AI remains secure even against the most sophisticated attacks. Don't forget to look in the description for the study link and let us know your thoughts in the comments. What innovations do you think could further enhance AI resilience?